Good morning, good afternoon, or good evening, depending on which part of the globe you may be watching this from. My name is Scott Clark, and I'm going to be talking about some things about coils and various aspects of things that are used to classify and characterize fields, and how a trigger coil producing a field that repels a magnet that is like pole oriented, and how the positioning, what it relates to, and where the timing aspects come in, and the types of control systems. Of course, first of all, this is just a simple coil, pretty much the easiest type of coil to make. Fields are oriented vertically in this case because that's the position of the cylindrical aspect of this coil. But the center of the coil actually is where the flux force lines are concentrated in a projection. Of course, when it comes up, it kind of rolls over in a sense. But in essence, those fields are measured with devices such as Gauss meters in order to determine the field strengths, and a unit of measure that can be used to clarify these characterizations of what exactly occurs between a system that is interacting with each other. And what I've done here is set up a power supply, an external power supply. This is just for demonstration, and it's a variable power supply at up to 7 volts. 7.5 volts, and what I'm doing is monitoring on a voltmeter. So basically, even when the coil is under load, it basically is being measured, the voltages and the Gauss metering aspects. And that's my scope meter over here. So that's monitoring that. With the Gauss meter, what I do initially is use this probe, which has a very thin piece of metal, flat piece of metal, that primarily measures in the up and down direction from the flat. In a sense, that's the primary measuring direction. So when I put it into this coil, or under the plate, first I measure from the top of the coil. So by placing it directly on the coil between the gap, I can actually get the measure not of the magnet itself, which I've did surface measurements of like 30,000 Gauss on these 3/4 inch neodymium magnets. But when you're talking about the distance relational separation, there is a change. So basically, the field strengths are not the same as if you were on the surface of the magnet. So what we're looking at here, first of all, is a stationary aspect of turning a heavy plate that's on a bearing system and such. So there's really not a lot of drag, but you can see it just takes a little bit of force with my finger to be able to move it. But that's one of the primary aspects too, is if you have a high drag force, that actually will work against you, other than the fact that when inertia of a heavy plate in motion is spun up, then the inertia is carrying that mass so that it actually will keep it going in its mass inertia momentums. But in this case, we're just looking at what the fields will be required, voltages and currents, with a basic coil that is like 75 foot of 26 gauge wire. So, you know, it's not a real heavy wire, but it's able to handle some current, which is able to run without getting burned up. If you run too much current, it will melt through the enamel and short the thing out. But getting back around here, where we make comparisons to how much force it takes to actually move this in a dead stop position, it actually will take less force in field strength to keep things going than it does from a dead stop, because dead stop has no inertia. So otherwise, when I take my measurement with the probe, I will compare that to the voltage being applied, and even in the dead stop position, even the aspect of what the field strength is at the top of the coil is representative of forces working in an interactive way. So even as this thing spins faster, the fields it's actually inducing will have to be counteracted by a force of electrical potential. So there's a aspect there, even though this coil is only actually around a 3 to 4 volt coil at 4800 RPM with these neodymium magnets on this flywheel. So basically there is a aspect of that too, an electrical aspect to counteract in high speed. So there is an amount of potential that has to be applied. But if you're taking it from zero state, that could be, as what you might say, a starting baseline of what could be used to classify and characterize these coils, so that any coil, when you're setting it up, will be able to be determined what you need to apply, how long you need to apply it, and timing and the duration and the intensity are critical, and optimizing the efficiency of field force energy used versus energy created. So anyways, I think that's all I'm going to really put into this right now for this demonstration. I know this is only like a 7.5 minute little video, and I could be elaborating further, but this is just a starter, give you a little idea, something to roll around in your mind. Of course, if we want to get into the deeper end of the pool, we can talk about the electron mobilities and flux amplification, which is something of another aspect of where geometry alone can even influence the differences in what field strengths can make. But we also have things such as eddy currents and aspects of mass, relationships to heat, so that there's nothing that's going to burn up a coil in that method or manner as well. So it's a rather complicated interaction of all these things. Anyways, it's going to be about 8.5 minutes now, so we're just going to call it for now, and hope you enjoyed this video. You're welcome to contact me via Facebook. Alright, we'll talk to you later.